Introduction to Dante, part of the Dante Certification Program, Level 1, Section 1. First, a bit about Audinate. We are headquartered in Sydney, Australia. We are founded by and employ many network engineers who deeply understand how networking and network standards work and how to best maximize performance for audio. We developed Dante as a 100% interoperable solution for all audio manufacturers. In this respect, we are unique. We offer the same technology to everyone, ensuring that every product that uses Dante could freely connect to any other, no questions asked. And what do we make? We are the sole creators and developers of Dante audio networking technology, and we make all of it, from hardware modules and chipsets, sold to manufacturers in order to quickly and easily integrate Dante into their products, development tools for manufacturers, allowing them to customize Dante to suit their needs and designs, and software products that allow audio professionals to use Dante, such as Dante Controller, the essential tool for managing a Dante network, Dante Virtual Sound Card, software that lets you use any digital audio workstation you prefer directly on a Dante network, and Dante Via, another software product that allows you to put connected audio products and applications directly on a Dante network. We'll start with a refresher on the basics of digital audio. There are a few key concepts here that help us to understand how Dante works and how to understand requirements surrounding subjects such as bandwidth or latency. When we convert analog audio to digital, the analog signal is sampled at constant intervals of time. At each interval, the amplitude of the analog signal is captured and then represented as a number. This method produces a stream of values in time and is known as pulse code modulation, or PCM. It is the most common format for digital audio and has been used in CD players since the very beginning. PCM audio itself is uncompressed by definition. The sample rate is just what it sounds like. How fast are the audio samples being taken? The math tells us what to do here. The Nyquist theorem states that if samples are taken at least twice the maximum analog frequency we wish to capture, then we can faithfully reconstruct the entire signal. Now, human hearing is generally agreed to be in the range of 20 Hz to 20 kHz, which indicates that a sample rate of 40 kHz is sufficient. However, in practice, this rate is pushed up to 44.1 kHz, the old CD Redbook standard, or to 48 kHz, the most common value in pro audio, as these values fit nicely with the frame rates used in film and video standards. Higher sample rates allow for higher frequencies to be captured. Bit depth determines how accurate each audio sample can be by determining how many possible values our scheme can represent. If, for example, I were to use only 4 binary digits, 1s and 0s, to represent my audio, the table here tells me that I'd have only 16 possible levels of amplitude with which to represent each sample. Not very good, really. Recall those old video game soundtracks, like on an old Atari console? Those were 8 bits of resolution, or 256 possible levels of amplitude. The CD uses 16 bits, and we all know how that sounds. It's really quite good. And that allows 65,536 possible values. When we jump up to 24 bits, we see that we have 16,777,216 possible values. From a purely technical perspective, increasing both sample rate and bit depth will improve the absolute fidelity of a system, as they each represent more data per second being captured. There are many differing opinions regarding the human perception of audio, and Dante does not impose any judgment in this regard. It does make sense that increasing both sample rate and bit depth will increase the bandwidth required to transmit the signal. A higher sample rate means more samples per second, and a higher bit depth means that each sample is that much larger. For this reason, many products that support multiple sample rates offer reduced channel counts at higher sample rate values, as they are constrained by the rate of data they can provide. It now makes sense to think a bit about bandwidth, that is, the amount of data required per second for digital audio. Note that this slide concerns pure digital audio only, not network bandwidth per se, which is calculated differently, although they are related. Bandwidth is easily described for one channel of audio. It's simply the sample rate times the bit depth. So let's see how some common values stack up. For a common Pro setup of 48 kHz and 24-bit depth, we get a value of 1.152 megabits per second. For 64 channels of audio at this setting, the audio bandwidth is still only 74 megabits per second. Now, consider that a gigabit connection on a network provides 1,000 megabits per second, and it's easy to see that even with other areas of network overhead accounted for, we still have plenty of bandwidth to work with. An important note: in Dante, multiple channels of audio are efficiently packaged into what we call flows, and so do not have a one-to-one correspondence with the bandwidth required for a single channel of audio. Still, this is indicative of the amount of bandwidth required. The word clock is the clock that determines how data is interpreted in a digital system. Once audio has been sampled and is represented as a series of digital values in time, we need to make sure that all the devices in our system agree about how to read those values in time. They need to agree about when each sample begins in that stream of ones and zeros, so that the values can be faithfully converted back into analog signals. For this reason, digital systems always rely upon a single clock master as a point of reference. Let's now look at an example of a severe word clock failure. Here we see two devices labeled A and B. They're each receiving the same stream of audio data, but the devices are not interpreting the values in the same way because there's a shift of 1 bit in time between them. Now in the right-hand box, a word clock, represented by the vertical bar, organizes the data so that both devices agree about when the digital audio sample begins, and so each reads precisely the same data. Now clearly, devices must agree about how to interpret this data in time, or we really have no audio at all. In a Dante system, such a catastrophic condition would be considered a fault state and audio would stop. Also note that this example illustrates a severe clock failure for illustration purposes only. Systems that interconnect digital devices use special data formats to make this particular scenario impossible. You've probably heard the term jitter, and you may have heard actual jitter. Jitter is a type of distortion that results from word clock being inconsistent. The samples are no longer played out exactly when they're supposed to be. This is recognized as a potential problem in legacy transports like AES, MADI, or ADAT. In these systems, the word clock is embedded in the audio signal as a start-of-frame message, which must be unpacked from the data stream, which contributes to misalignment under some signal conditions, especially when connecting many devices together. Now, the classic solution here was to use an expensive external clock that would slave each device and thus force clock alignment between them. Dante uses a highly accurate clock synchronization method that ensures outstanding jitter-free performance for any number of connected devices without the need for any external clock sources. Latency is an issue in all audio systems. It's simply the delay incurred by the transport and processing of audio signals. This is really only a problem in settings where the delayed and undelayed signals are heard simultaneously, as in a recording studio when doing overdubs on a digital recording system, or perhaps floor wedges on stage that are combined with the sound of live instruments. Of course, audio latency is very pronounced without any electronics at all. Since sound travels at about 343 meters per second, that means that each 34 centimeters requires about 1 millisecond of travel time. This air travel delay is why we use towers to align speaker output with the heavily delayed audio coming from a stage in an outdoor concert. If you'd like to hear what a sound system is like with 2 milliseconds of delay between sources, simply stand in the middle of two stereo speakers and then just move 34 centimeters to the left of the right. You've now created a 2 millisecond offset between them. In earlier audio networking solutions, such as VoIP, high latency was a real issue. As we'll see, this is an area where Dante gives you complete control. Let's summarize this section. Digital audio works by playing out or recording samples. The bit depth describes the amplitude resolution, and the sample rate determines the maximum frequency that the system can handle. The word clock is key to the accurate transport of digital audio because it's all about data being processed as a function of time. This is why Dante uses a clock distribution scheme that is designed to be robust and tightly synchronized even between hundreds of devices. Networks can easily transport digital data. As we'll see, time is part of the special sauce that Dante brings. Please continue to Section 2 of the Dante Certification Program, Level 1.